Good morning, everybody. Work got me a new iPad because my old one's battery is having trouble. So this is the first time I'm using it. Never, ever use beta equipment in a production environment. That's the rule. So I broke it this morning. But we'll see. I've got my old one here just in case, right? But let me know if there's any technical difficulties, things don't show up on the screen, or any recordings happen to be bad. Okay, so gravity and energy. So the concept what we're trying to tackle right now is conservation of energy. How do we apply it in a world, in a universe where the things that we thought we knew, we actually don't know very much about. What do I mean by that? How did we do gravitational potential energy before today? mgh, right? It all comes down to work, okay? And so the work done by gravity, okay, is force times distance, right? And that force before we knew as mg, right? And then the distance that gravity would pull things, it was the vertical height, mgh, right? So we just called that work and we said, you know what? We're just going to call this potential energy. And then we ran with it, right? We had all of our work others plus energy initial equals energy final, right? All of that, so this master equation still holds, no problem, okay? What's the problem? Well, yeah, when we're no longer on Earth, or maybe even just, a little bit further up away from the center of the Earth, there's a problem on the screen. Does anybody know what it is? It's little g. What's wrong with little g? It isn't constant, right? Didn't we find that like little g was something like that? And so little g depends on how far away from the center of Earth we are, or center of any planet, center of the moon. So if little g is no longer constant, and we want to be able to do conservation of energy, because again, conservation of energy comes with benefits, right? If we don't need to know the acceleration, if we don't need to know the force, we just want to know, like, how fast is something going if we drop it off the International Space Station, or how much speed do we need at launch to be able to get from a certain height, right? All of these questions don't require us to get into the nitty-gritties of acceleration and force and time and all that stuff. We can kind of shortcut all of that by using conservation of energy. Problem is, we need to be able to write down mgh in its more universal form. So we're going to skip it, but basically what you have to do is you have to do some integrals. And why do you have to do some integrals? Yeah, right? The little g changes, right? Little g is dependent on how far away we are, right? So we do a little bit of integral magic. It's not a big deal, but I've got better things to do today, right? And what we find out when we apply all of this, right? And we correct for the fact that little g is no longer constant. I hope it comes as no surprise that the quote-unquote real gravitational potential energy, what g do you think might be in it? That's big G. Okay. That's where all the good news ends and the bad news starts, because this gravitational potential energy is going to start with a minus sign. I'll explain why this thing is here in a second, right? But it starts with a minus sign. That minus sign is going to be, I don't know if confusing is the word. It's going to haunt you as you do your math, and you're like, why am I not getting this right? And I'll say, did you put a minus sign on it? You'll be like, ah. So negative big G, M1, M2 over R. There it is, okay? That right there is the true way to do gravitational potential energy. I say that just, so there's some caveats and some asterisks and footnotes on that. We'll get to that in a second. I want to start with all of the problems with this equation, okay? First problem is the minus sign. More on that in a second. Ignore the minus sign. What does that look like? When you say gravity, what do you mean? Didn't we do this already? Right? Like, was it right? Yeah. Why did that not center? Right? What? Don't we have a big G mm over R thingy? Right? Notice, what's the difference between that force and my statement for gravitational energy right here? Yeah, the R, right, is not squared. Do you want to take bets on how many times I've made that mistake in my career? Right? I have a hard time remembering squareds, period, right? And so it's very easy for me to flip-flop force for energy. So don't be me. Don't make that mistake, right? Be really, really careful in this 1 over r versus 1 over r squared. Because otherwise it practically looks identical, doesn't it? Right? So watch out, okay? What are the units of this thing here in the box? It's got to be joules. Why does it have to be joules? Because I said it was energy, right? Okay? So this comes out as joules, but if you put an r squared in the bottoms, somehow it comes out in newtons. Crazy. Okay, so that's one problem. But I mean, I guess a pro there instead of a con is that it is a little bit easier to remember. Like a lot of these equations are similar. It can be both a pro and a con. All right, the minus sign. That minus sign is an artifact or a feature of a rule. The baseline is, which way does gravity point? Inwards, towards, it attracts. And that minus sign is really telling us that, okay? But you're like, Mr. Balogh, energy doesn't have any direction. It's scalar, right? It was one of the big features of energy we liked. We didn't have to do vectors. Yes, I know. But unfortunately, we are not allowed to choose 0 for this one. Remember how it was a big feature when we were setting up conservation of energy problems? We had to do initial, we had to do final, and then we had to decide where our 0 was for gravitational potential energy. And we could put it wherever we wanted, right? That wasn't the issue. This time, with this equation and the way that it's been derived and set up, we are not allowed to pick 0. 0 is chosen for us. So where is it? Where would it be nice to have it? At the center of the planet? Okay, fine. We put 0 in for r. Like we're at the center of the planet, we put r equals 0, what do we get? Undefined. It's a mathematician's answer. Right? They're just being scared of something. When you divide by something that's getting really, really small, what do you get? Nope. When you divide a number by something that's really, really tiny, it gets big, doesn't it? Okay? And it grows to infinity. I don't understand in math why all of a sudden it becomes undefined, right? I think mathematicians are just scared of infinity. Infinity is a great place. It's kind of a bluish gray. I understand what the mathematicians are trying to say. They're saying that there is no algebraic or mathematical manipulation that can define the function or relationship between the thing. Okay, fine. But that's not what's happening, right? We're dividing, as we get closer and closer to the center of the earth, we're dividing by things that are smaller and smaller and smaller, and that would then get bigger and bigger and bigger, and then all of a sudden at 0 become infinitely large, chaos, cats and dogs living together, mass hysteria. So we're not allowed to put 0 at the center of the planet, okay? So where are we going to put 0? Okay, let's look at this function. How do you get the potential energy to be 0? Can you change big G? No, that one's set. The universe, right? This universal constant, can't mess with that one. I mean, suppose we could play with the masses, right? Oh, 0 mass, we're done. Okay, fine, you're not a photon. Okay? Everything else in the universe has mass. So we can't really, we can mess with the masses, but we can't set them to 0 to say that thing's 0. So the only other thing we have is this distance from the center of the planet. So in order for this gravitational potential energy to be 0, what does R have to be? What? Really big. What's another way of saying really big? Don't be scared of it. Blue-green, right? Or gray-blue, right? It's infinity. When R gets to be infinitely large, what happens when you divide by an infinite number? You get 0, right? No, it's not undefined. It probably is. We need a mathematician. No, we don't need any mathematicians. Okay? So, where is 0? Need to draw Earth. So, there, okay. And then we need some blue-green stuff. Sure, why not? Florida. Can we take Florida off? All right. So there's Earth. You know it's Earth because it's blue. So if I don't know if you're standing, this is not the scale, right? Okay. And this is you got the very center, right, of the Earth, and we're doing like a distant. I won't draw it from the center, but I'll like draw it from off to the side here, right? Okay. So this is our R, right? Then gravitational potential. If I ever write a big U, sorry, it's the symbol in physics for gravitation for any potential energy is capital U. So if my gravitational potential energy is 0, then my distance is infinity. Now, we talked a little bit about infinity last time, right? Infinity is terms of how far away is infinity. Well, the answer is that depends. Because, again, I'm infinitely far from the table, gravitationally speaking, right? Okay? There isn't any, I'm not feeling that gravitational force. But I'm certainly not infinitely far away from the Earth. I need to get far enough away from the Earth so that the Earth is no longer having a significant push or pull on me, right? And the answer to that depends, well, what else is in the solar system and where is it, right? In the case of getting to the moon, we get close enough to the moon where Earth's gravity becomes small enough that we don't have to worry about the calculations anymore. If the Earth were alone in the universe, then the answer would be it has to be infinitely far away, right? But in all practical purposes, well, we'll talk about how to get infinitely far away here at the end. But the point I'm trying to make is come on. Why can't I access the properties of my tool? I don't have my, you can see the dot, right? Okay. If I'm using this equation, then I have to use infinitely far away, right? In order to make it work. Okay. So if 0 is up there, infinitely far away, that means no matter where I am, whether I'm like at the surface of the Earth or higher on Everest or the International Space Station or anything like that, what sign is my energy going to have? It's going to be negative, right? Whenever we're below 0, right, we have negative energy. Now, just because we have this always fries my brain. I don't know what it is about my brain that I can't really hold this idea in my head, right? Okay, so I don't know. I'm just going to make up some numbers. Okay, so let's say that we're standing here on the Earth and our potential energy gravitational, I don't know, is negative 10,000 joules. I didn't calculate that right. I'm just making up a number, right? If we go up to where, say, the International Space Station is, right? Which again, looks like a TIE fighter. May the 4th be with you, even though it's the 6th. If we're up there, is our potential energy bigger or smaller? Higher or lower? Like what number? Let's say this is, I don't know. Again, I'm totally making up numbers. Minus 8,000 joules. What? Okay, which of those two numbers is higher? Larger? I don't know about you, but my brain completely erases the minus sign and just looks at the 10,000. 10,000 bigger than 8,000. That's wrong. The higher number here is the least negative one. So if we change our potential energy, if we go up from the surface of the Earth, have we gained or lost energy? We've gained it, even though the number has gotten smaller? Yes. It just, I have to think about that one for a while, right? I had to be very quiet and think about it before I convince myself that that's actually the case. All right. And you can do some calculations if you want to prove that it's true. But nonetheless, it's true. The smaller the negative number, the more gravitational. Okay, so what is that? So when we're sitting on the launch pad and we want to get off the surface of planet Earth, is our potential energy zero there? No, right? We now have potential energy at the launch pad, right? And when we get to the International Space Station, do we have gravitational potential energy there? Yes, right? So just, it's weird. I didn't invent the universe. You can take it up with the management. Okay. Everything up to this point applies whether or not you are in orbit. Okay? It makes absolutely no difference whether you're going into orbit. But what I want to do now is I do want to start talking about, okay, what happens when you go into orbit. And so we have to add, right, if we are in orbit around something, okay, yeah, there we are. For whatever reason, we have no spaceship and no International Space Station or anything, right? And we're in orbit now. We know our orbits are going to be circular. And what else do we know about orbits? What has to be happening in order for us to be in an orbit? Gravity has to be there. Done. Other key, really important thing about an orbit. Well, yeah, but we're not, I mean, yeah, we're falling kind of fast, but we've got to be moving sideways, right? That's like key. If we're not moving sideways fast enough, then the curvature of the planet doesn't have, okay. So we have velocity, right? That tangential, the orbital velocity, okay? Orbit, all right? And, okay, that means that our total energy, right? The orbital energy that we have, okay, is going to be a combination of two things. What two things? We're moving and we are not at zero gravitational potential energy. So what two things are we going to put together here? Kinetic and potential energy. Well, what's kinetic energy? Mathematically, like 1/2 mv squared plus, right? Our total orbital energy is going to be a combination of kinetic energy plus potential energy. But we're going to write plus what? Negative big G m and then big M all over R, not squared. Okay. Okay. Orbital mechanics is hard enough. I don't know about you. I don't want to spend the rest of my life trying to keep track of 1/2s and M's and V's and big G's and other M's and R's and all over the place. It would be really nice if there was a compact form that we could write this down in, right? My orbital energy, can I simplify this? And the answer is yes. And believe it or not, I'll show you a bit of mathematical trickery here. We are going to be rescued. It's totally, this is out of pocket. You wouldn't expect this, okay? We're going to be rescued by Newton's second law. Now, normally, as soon as Newton's second law gets involved, game over, right? Life is hard. We're in statics. We're in dynamics. Oh my gosh, there's forces, there's equations. I got to develop everything. Ah! Right? No, this time Newton's second law is going to help us. We are going around in a circle, so we know something about the acceleration, right? It's going to be v squared over r. And then that all has to be equal to a force, right? M equals sum of the forces. The only force is gravity. And so I'm just going to write. Now, I'm only going to do this like in magnitude terms. Gmm over r squared. There's my force. Okay, so we last time we did this, we kind of played around with this and we got little g. I don't want to start getting rid of things that I might need. Okay, so what I'm going to do is I'm going to take this mv squared over r equals gm. I just rewrote the line. Okay, I'm going to take that and I'm going to multiply by 1. This is a famous mathematician's trick. It's very clever, actually. Okay, how am I going to multiply by 1 this time? And you're like, Mr. Bailey, you just multiply both sides by 1 and you get right back to where you started. I agree. I'm going to multiply by 1 by multiplying both sides by the same thing. There, I multiplied by 1. And you're like, no, you didn't, Mr. Bailey. You multiplied by r over 2. Yeah, but I did it to both sides. And so ultimately, what could I do? And I'm right back to where I began, right? Okay. Mathematicians say this is multiplying by 1. I kind of disagree, but it is really, really cool. Where did my... I think my new iPad just deleted my whole slide. No, it's right there. Why did you do that? That was weird. Still working out the bugs. Okay, so I multiplied by 1. And you're like, but Mr. Balogh, that really didn't get you anywhere. Ah, but it did. Because on this side, I can eliminate my r's. And what am I left with? Right? And then on this side, I end up wiping out one of the r's on the bottom, and I end up with big G mm all over 2r. So it turns out that big G little m times big M over 2r is exactly equivalent to 1/2 mv squared for something that is doing a circular orbit. Which means I can now chuck this up into heat. Whoa. Darn it, why do you keep doing that? It keeps deleting the slide. Bring it back. I said bring it back. This is a bug that I am not going to be very happy with. There it is. Can you guys see it? Yeah. I don't know why it keeps doing that. Does anybody ever have that happen to you in GoodNotes? Where it just wipes out a page all of a sudden? Okay. Yeah? All right. Talk to me later. There's something going on here. All right. So I'm gonna substitute that in right there. They did it again. As soon as I hit undo. I don't think so. I do have a fancy Apple Pencil Pro that wants to be squeezed or something like that. But Turn off what?
If you press down on it, so that take off that setting. Because if you squeeze it, it pulls up a bunch of settings.
I turned that off. Yeah, where it does the little radial menu. No.
You don't have to squeeze off.
Double tap, squeeze, switch between current tool, but like it's wiping out the whole thing. I don't think. Well, let's see. Let's see what happens. Technical troubleshooting on the fly. Guys learning a lot, right? Or maybe you're just sitting there going, "My teacher's an idiot, doesn't know how to use this stuff." All right. I tried to make all the settings. They wouldn't let me just do the Vulkan Mind Meld thing with Apple products. You know how you can like take a Apple product? Some of you know this. You put one, you get a new one, you put the old one right next to it, and it says, "Oh, do you want me to just like copy this, like Vulkan, like shroomp them together?" And I'm like, "Yes." Work has installed new software that's supposed to like track me and report to the CIA and do whatever it wants to do, right? But like, it's Work's device, so they're allowed to do that. But it meant that I couldn't just my stuff over. It was really annoying. Anyway, where are we? Energy of an orbit is going to now be, instead of 1/2 mv squared, big G mm over 2r minus big G mm over, what do I have here? If Bob has half an apple and Sally has -1 apples, how many apples do they have? -1/2, right? So to write the energy of anything that is in orbit, so this is a combination, right, of kinetic and potential energy. This is the total energy something has in an orbit. It's just minus big G mm over 2r. Add that to our orbital toolbox, right? That's pretty nice, right? To be able to, we went from kind of big messy thing up at the top to a more elegant, concise, compact way of writing an orbital energy. And notice, do we need to know exactly what the orbital velocity is in order to write? No. What do we need to know? You know what universe we're in, big G, right? We need to know the mass of us or the spaceship or whatever that's doing the orbiting, right? We need to know the mass of the planet or moon or whatever we're in orbit around, and then how far away from the center of that body that we are, right? If we've got all those things, we know what our orbital energy is. And so if we want to change our orbit, we want to go higher or lower, we can calculate how much energy it's going to take, right? Do we have to gain energy to go up? Do we have to lose energy to go down? We can calculate those things, know how much propellant we need in order to change our energy by that much, calculate our fuel requirements, and then we're in Star Trek. Oh wait, warp drive thing, right? So pretty exciting stuff, pretty exciting stuff. So let's finally do this example that kept flashing on the screen just as my slide would delete itself. Okay. All right. A lot of times we encounter a wall of text and it can be hard to sort of like absorb what's going on. I tend not to read things like right away in detail, right? I'm looking for key words. So like one of the words that's really jumping out at me right now is this altitude word. Altitude is a bit of a kind of a trick, isn't it? Is that altitude of 200 kilometers, is that our R? Is that our distance? No, right? Where do distances have to be measured from? Centers, right? Kilograms, what are they giving me if it's a kilogram? Some sort of mass, right? And then I've got another altitude word over here, right, at 100 kilometers. So, right, now I can finally, like, I've identified the honeypots, the traps, right, that are sitting there waiting to engulf me. So can I maybe now grok the question, what the heck is going on? So we have orbiting, right? So I instantly, before I read anything else, I'm just going to draw a picture, like my bog standard picture of an orbit, right? So there's the planet. It says it's Earth, so we'll label it Earth, right? And it's a satellite, And so all satellites look like TIE fighters, right? And sometimes I draw like the circular path that it's going around. So I've got something in orbit. Do I know anything about that orbit? The orbital altitude is 200 kilometers, right? So like I know that the distance from the surface to the satellite is 200 kilometers, but I got to be careful, right? Okay, so air resistance is causing this thing to lose altitude. I start to panic a little bit because friction's involved. I'm a little bit worried, right? Okay. But it says that over time it drops, right? It loses altitude because of this atmospheric friction, right? Drops into a lower altitude that has a distance of 100 kilometers. What am I doing right now? Like what step? This is visualized, right? I'm just getting a picture. You could do a list if you want, if that works better for you. But for orbital mechanics, pictures for me do a lot, okay? And then they want to know initial and final orbital speeds of these satellites, right? So for part A, right, what are the orbital speeds, right, for these different altitudes of orbits, okay? We know something about this, like conceptually, right? Where is this satellite going to be going faster? Remember, orbital mechanics was weird, wasn't it? The lower it is, the faster it goes. Okay. I'm now bothered because it's said that air friction, right? The atmosphere's friction on the satellite is causing it to lose altitude. Right? That makes sense, right? But friction is making it speed up? The answer is yes. This is exactly what happens, okay? I don't want to prove it to you, but I'll just say orbital mechanics is weird. Okay. Do we know the orbital velocity? Do we have an equation for orbital velocity? Yeah. Back when we did our toolbox, right? For orbital stuff. Oh, danger here of wiping out all of my slides. Where was that one? Is it here? Yeah. Yeah, that was Kepler's laws. This was our orbital toolbox, wasn't it? Okay, so this being our orbital toolbox. Oh, look, it's right there, right? Velocity of the orbit is equal square root of g(m)m over r, right? We could now add into this toolbox, right? We can add in the energy of an orbit is equal to negative g(m)m, what was it, 2 over 2r. We could do kinetic energy, right? 1/2 mv squared, but it's also equal to g(m)m over 2r. That's a little bit confusing, but it's true nonetheless. And then did we get all? We got all of them. Oh, yeah, all this is circles only. We got all that. Okay, yeah, I think our box is pretty complete there because this is the orbital mechanics slide. You could add in, right? You could add in this. Every time I put my palm down, it moves. I thought I turned off all of these gestures. You can add, so this is, I'll say not just orbits. Okay, so that, right, universal law of gravitation, little g, big G, just kind of complete the toolbox for chapter 13 here. What are we missing? Oh, gravitational, that was sloppy. M over R, and I think we kind of got everything there, don't we? Yeah. All right. So the toolbox has expanded, and we know what our orbital velocity. I've forgotten it now. Square root of big G over M over R squared. I didn't pay attention. Just over R. Square root of big G M over R. Okay. So to calculate the orbit for the 200-kilometer orbit, right, we put in big G. 6.67 times 10 to the minus 11. What mass are we going to put in here? We're going to put in Earth's mass. 5.9. Why Earth's mass? Because we're orbiting Earth, right? In these orbital mechanics things, a big mass means the mass of the thing that we are orbiting, right? And then, so what are we going to put in for the distance then? Altitude plus radius. So what's the radius here? It's 6,370 times 10 to the 3 meters, or 6.37 times 10 to the 6. I tend to remember 6,370 kilometers. And then plus 200 times 10 to the 3 meters. Again, where are the 10 to the 3s coming from? 6,370 kilometers is 6,370 times 10 to the 3 meters, right? The kilo just helps us not have to write times 10 to the 3, right? And 200 kilometers, I can write as 200 times 10 to the 3 meters. All right, don't square that, but square root it, do all that stuff. And I got for the 200, I got 7.79 times 10 to the 3 meters per second. So that's 7,790 meters per second. 7.79 kilometers per second. That's pretty impressive. That's a fast speed. And then for the 100, do the same calculation, but just make sure that the radius is different. I got 7.85 times 10 to the 3 meters per second. Indeed, this thing sped up, right? The atmospheric drag and friction dropped it into a lower orbit, and it sped up. Okay, and then now for part B, they want us to calculate the change in orbit. Yes? No, I'll give you all the constants you need, right? You don't have to put those on your cheat sheet. They've been embedded in my brain over the years. But yeah, no, remember, if you need a constant, and if you think I forgot to give it to you, just come up to me, right, and ask me for it, or put your hand up. And then if I realize I just forgot to put it on the exam, I will write it on the board. I'm panicked because I wrote your exam this morning, and I'm trying to remember if I did that. But I already sent it to the print shop. So this is going to be exciting. We're going to find out. I will post the topics hopefully tomorrow if I get time. I got to write a 4B exam later today. All right. What am I doing? Oh, calculate the change in orbital energy. What are they asking me for? Change. Whenever you see the word change, what symbol do we use? Delta, right? So this is the delta energy of my orbit, which means delta always means what? Final minus initial, right? So whatever my final energy is minus my initial energy. Okay, so that means I got to calculate two things. I got to calculate my final orbital energy. Final, so initial's up here, right? Final is down here. It started at 200, it goes down to 100. So to find my final orbital energy, well, I now have an equation for my orbital energy, right? My final energy is negative G mm over 2R final, right? So again, I got to throw numbers in now. Negative 6.67 times 10 to the negative 11, that's big G, times my mass of my satellite, 100, times the mass of planet Earth, 5.98 times 10 to the 24. Your fingers are going to get a workout on your calculator. They just are. Use engineering notation where you can, if you know what that is. All right, divided by 2. And then I've got to get, this is 6. Can I just write 6570 times 10 to the 3? Will you guys be okay with that? No? No? I just bamboozled you there. 6370 times 10 to the 3 plus 200 times 10 to the 3. What happens when you add 6,370 plus 200? 6570. All right. And when I calculated that, I got negative 3.08 times 10 to the 9 joules. Okay. And then I do the same thing, but to calculate the initial energy, what changes? Everything else is the same on top. What changes? It's just the R, isn't it? That squiggle up there on the top is L, that's the same. I didn't want to rewrite all those numbers. And I got negative 3.04 times 10 to the 9 joules. So when I come in here and I take that difference, okay, I take my final minus my initial, the number I got was minus 4 times 10 to the 7 joules. Okay, my change was negative. What does a negative change in energy mean? Did we gain or lose energy? The negative sign means we lost energy. Why did we lose energy? We went down, right? Okay. If I take this and if I take my keys and I drop them, right? Do they gain or lose gravitational energy? They lose it, right? It starts with higher potential energy than it ends with, right? Same thing happened here, right? We lost energy because we went down, okay? Even though zero's way up there, down is still down, all that kind of stuff. Question? What was that? Oh, jeez. Because I'm an idiot. I got too excited about adding things. I need to change the size of this eraser. And like none of my contextual things are popping up, which is really weird. All right, we'll try this. So the final is 100. Thank you so much for correcting me. And my initial is 200. These numbers are correct, though. Please tell me those numbers are correct. Yes. Yes. I just had them out of order from what I was doing on my notes. And this number is also correct. So in a strange turn of events, my numbers are correct this time. But my equations, the numbers went into them, were not. But now it's all fixed and the screen is not lying anymore. Thank you. Jershan, did you have a question? Same comment? Thank you. It's losing energy because of that. You'll notice some people always ask, well, Mr. Bailey, you didn't put friction. Where's the work other, right? I'm not like calculating a full like work energy thing. It just asked me for what's the change in energy between these two orbits, right? And I calculated that. The reason it lost energy, where'd that energy go? It went into air friction.
Wouldn't it also be a little advanced for us because the lower it gets, the more friction, so it'd be constant?
It gets really bad, which is why we're using energy and not another different method. Because we could use rotational kinematics for all kinds of stuff. Nice thing about orbital mechanics when you're dealing with energies is that you can sort of bypass all of these very horrible things that are going on. And it's like, it is amazing it still works. Where it starts to fail is when there's enough air friction here that we are no longer in orbit, right? As soon as our orbit gets to the point where the eccentricity gets large enough and it starts to, the perigee intersects the surface of the Earth, well, then we're coming in for re-entry, and that's a totally different ball of wax. All right. Ball of wax, ball of yarn, I don't know. Whatever the idiom happens to be. You are probably at the point where you are saying, you're at that point in the semester where you're done. You're done. Mr. Balogh, I was done several weeks ago, right? I can't believe I'm still here. Maybe you are done with work. Maybe you're done with this planet where just things are just so bad and you want to get away, like permanently, okay? Beam me up, Scotty. There is no intelligent life down here, right? So how do you get away? Okay, well, first of all, you need a rocket, right? And you need to load the rocket up with supplies and all that kind of stuff. But we are going to answer the question, how fast do you need to launch something in order for Earth, Moon, Sun, any orbital body, in order to leave it behind, in order to get out, right? And not fall back. So this isn't a question of like orbits. This is literally, if I just launch straight up, how fast do I have to be going at launch to escape? So that gravity cannot pull me back down. So we need a picture. There's the Earth. Here's our rocket ship, which when I draw them always look like carrots. And then we want to get far enough up here with our rocket ship, right? So that we will no longer come back. At this point, we want our velocity to be 0. Because what we want to do is we want to calculate the minimum speed required to just get away. If we have more speed, then we have extra energy up there and we'll just keep moving, right? But as far as like a minimum escape speed is concerned, we want to get to the point where our kinetic energy is 0 and our potential energy is also 0. And why would our potential energy have to be 0? Remember, gravitational potential energy is 0 when we are infinitely far away from the planet. Okay? So we're going to calculate how fast do we need to be going initially at launch in order to get to a condition where our total energy with respect to planet Earth is 0. Okay, so this is a conservation of energy problem. Work other plus energy initial equals energy final. This applies not just for escape speed, but for any speed, right? You could reverse this problem and drop something from a height and find out how fast it's going. This is how we calculate like meteor impacts, right? And stuff like that. We calculate their speed based on how fast they're going and how far away from us they are and all that kind of stuff. We are going to ignore the fact that there's any atmosphere. Dangerous, but just makes life easier, okay? Initially, do we have any energy? We ask the question, are we moving at launch? Yes. Okay. We could add in the energy of the rotation of the Earth. We're not going to do that. We're going to pretend like there's a static Earth, or maybe we're launching from the North or South Pole. Who knows? Okay. We'll get back to that in a second. But the reason we're not going to say we have 0 initial energy is because I asked the question, how fast do we need to be going at launch, right? Initially, in order for us to achieve escape velocity, right? So what we're trying to do is calculate, okay, yes, we are standing still on the launch pad and we will accelerate up to a speed, right? That just, we'd have to have extra speed at that point, right? To get it. We're imagining a situation where we're launching, having a speed. Once we have that speed, can we make it away? Which I know it seems a little bit weird, but our kinetic energy initially is not going to be zero, okay? I'm going to call this the escape speed, by the way. All right, so we do have initial energy at launch. But we also have gravitational potential energy at launch. Why do we have gravitational potential energy at launch? Because we're not at zero. Where's zero? Nope. Out, right? Up. Remember? Zero is way up here. Okay. All right. So I have negative g m m all over radius of Earth. Not squared, Mr. Balogh. I so badly wanted to put the squared on that. Okay. And what's our final kinetic energy going to be? Zero. I already said it. What's our final potential energy going to be? Also zero, right? And then I can maneuver some stuff around here. 1/2 mv escape squared is equal to gmm over raised. So what cancels? Mass of my vehicle. So while mass of a vehicle does matter for accelerations and all that kind, and the amount of force and thrust, and rocket science is pretty wild, as far as calculating how fast you need to be going at launch in order to get away from planet Earth, it doesn't depend on your launch vehicle. It depends on the Earth, which kind of makes sense, right? So let's maneuver some stuff around here. I've got a 1/2 that goes over, becomes a 2. Big G, mass of the thing that we're on, radius of the thing that we're on. That leaves me with a v escape squared on this side. But what do I do with the squared to get rid of it? Take the square root, and there it is. That number, whatever it is right there, is how fast I need to be going at launch in order to escape the Earth. Put the surface, put the radius of the Earth in there, put the mass of the Earth in there. I can find out what that escape speed needs to be. If I am in orbit already, right? Let's say I'm already 400 kilometers above the surface of the Earth. I can calculate the speed I need at that point in order to escape the Earth. So this number, by the way, when you calculate it for the Earth, is equal to the Earth, escape speed for the Earth, is 11.2 kilometers per second. Yes, I did the conversion for you. 25,000 miles an hour. So in order to escape, right now, surface of the Earth, you have to launch a vehicle and have it be going 25,000 miles an hour at launch. What happened to you if you went from 0 to 25,000 miles an hour in a second? Yeah, squish, like grape. Okay, like really. That's not going to happen, right? Because at most, the human body can sustain a G load of like 3 Gs, okay, for minutes to hours, right? Meaning you feel 3 times your weight or something like that. So we're not going to do this, right? This isn't like but we do know that in order to escape planet Earth from its surface, you do need to eventually, right, be going 11.2 kilometers per second. It could take some time to do that, right? But eventually we do have to reach that speed.
Is the 11.2 number purely vertical velocity?
Yeah. Well, no, it's a velocity. Okay, you don't have to be heading directly away. You achieve this velocity, Earth will no longer be able to pull you back.
So even if you're in orbit and you accelerate to that velocity going like in an angular motion, then you would get out.
Eventually your orbit would no longer be circular. It would achieve a hyperbolic orbit, which doesn't close on itself. And so, yeah, you're on your way. Which is, again, why we launch from where we launch from, right? We launch most of our rockets from Florida, okay? Elon Musk is launching his rockets from Texas, and Florida. Why there? They're south. Why do we want to be south? Why do we want to be closer to the equator? I mean, France launches theirs from French Guiana, which is down in South America. What is it about the equator that's different than, say, the North Pole? Faster speed. The ground is moving at like 470 meters per second sideways at the equator. How fast is the ground going at the North Pole? Nowhere. Okay, right? And so you start with some speed. Even though it's like at rest at the launch pad, you've already got some tangential speed to the side. This is why we also launch to the east, right? That's the direction of our rotation. Some people, this is disturbing. The sun came up over there today. It always comes up over there, okay, over the mountains. What direction is that? East. Which way are we rotating? Towards it. You're like, but Mr. Balogh, it goes this way. The sun doesn't go anywhere, right? We are rotating. Which way are we rotating? Towards the east or the west? We are rotating towards the east, okay? And then that makes the sun appear to go to the west, okay? So we are now going this way, right? And if we launch from Florida, or I was going to say Boca Chica, Texas, but it is now, as of yesterday, been Starbase, Texas, right? The people there voted to change the name of their town. Welcome to America. Launching from Boca Chica or Florida, the path of the rockets takes them over what? What's east of Florida? The ocean. What is east of South Texas? The Gulf of Mexico, not the other name. Okay? So, what's the positive thing about launching over the ocean? Yeah, SpaceX discovers if it blows up, right, the parts don't fall on very many people, right? The Chinese launch complexes are in the middle of China, and so when they launch, where do their rocket parts fall? No, on cities. Yeah. It's not good. They have an East Coast you could launch, but no, that's not what they decided to do. Okay, so escape speed for the moon, I calculated out 2.3 kilometers per second. So that's like a lot less than the Earth. Why is it a lot less than the Earth? It's not as massive, right? There isn't as much gravity there. So it's actually easier to get away from the moon than it is to get away from the Earth. That's pretty good. Mars, 5 kilometers per second. So again, taking off from Mars, less energy required in order to do it compared to, say, Earth. Now, there is a moon in orbit around Mars. It's called Phobos. Mars was the Greco-Roman god for like war, and he had companions, fear and death, or something like Phobos and Deimos, fear and dread. And so these two moons that have been captured by Mars are like really little. They're like asteroids. They're not even big enough to be spherical. Okay, so they have that asteroidy shape to them. I calculated, knowing the mass of Phobos, I calculated the escape speed of Phobos. So if you were standing on Phobos, you would only need 10.3 meters per second of speed in order to no longer be gravitationally attracted to Phobos. Meaning that as long as your spacesuit wasn't too bulky and heavy, if you got up to a nice sprint, you could like sprint in Phobos and jump, right? And then you would no longer be in orbit around Phobos. You would be in orbit around what? Mars. My advice is jump the right direction. Because if you have an orbital trajectory that takes you into the atmosphere of Mars and all you have is a spacesuit, good luck. That is not going to end happy. All right. That was the end of chapter 13. So guess what we get to do now? Chapter 14. Not leave early. No. No. And this is an abrupt change. It's like going from 5th gear to 3rd gear, going 65 miles an hour. So yeah, just wipe your brain, okay? And we're gonna get all the definitions out of the way here, if we can, so that we can jump into Archimedes' principle and Bernoulli's principle the next time we get together. So, fluid. What's a fluid? Not a solid. Good. I like that answer. In physics, it is both gases and liquids. The word fluid is a catch-all term for any gas and any liquid. They share a common feature in that their shapes changes, their volumes change. Solids are pretty easy to keep track of. Like a solid lump of metal doesn't necessarily change its shape on the fly, right? And tends to keep its mass together unless we're like exploding it or something. The problem with all fluids, be it a gas or a liquid, is that they tend to go places. Now, of course, as soon as I say fluid, the one fluid you think of is what? Water, right? Because it's common, it's everywhere, and all that kind of stuff. So I will kind of, meet you halfway here. Unless I tell you otherwise, if I say fluid, I'm talking about water, okay? I'll be very specific. I might say the fluid is air, or the fluid is honey or oil, right? Like I'll give a different material, okay? But just realize, and it can be a little bit weird, are you sitting in a fluid right now? Yes, because you are surrounded by air, right? So in physics, a fluid is any gas or liquid, distinct from a solid. Up to this point, we've done all solids. Nice, because solids don't change their shape and volume and all that kind of stuff. But if we're going to be able to do physics of fluids, we need to latch on to something that doesn't change in the fluid. If I take my water bottle and I just start dumping water out of it, right? Okay, the mass is changing, isn't it? I mean, the mass of the fluid mass in here is getting less and less, and the fluid's mass is getting more and more on the floor. It can be really difficult if we want to talk about the mass of the water in my bottle. So instead of talking about mass, what we're going to do is we're going to talk about density. That right there is the Greek letter rho. If I drew it really carefully, it would look a little bit like that, okay? R-H-O, right? Is how you pronounce that, right? But it's a Greek letter. I know it looks like a P. Sorry, I'm not responsible for this, okay? Take this up with all of the ancient cultures and people that stole alphabets from each other and all that kind of stuff, okay? So if you've taken like a high school science class, no doubt you've run into density, right? This isn't a major like coup d'etat, and I'm not showing you anything new here. But the cool thing about density that you may not remember or realize, and maybe your teacher didn't tell you, is that it doesn't change from volume to volume. In other words, if I have a swimming pool full of water and I have a cup full of water, which one has more density? It's identical, right? That's the cool thing about density. In fluids, in anything, but especially in fluids, it's the thing that stays the same. If I pour the water out, the density of water in here and the density of water down there are identical, right? Just like when we were dropping things, right? The mass of this and whether it's mass up here and it's mass down there were the same, right? Okay, and tended to cancel out. We're trying to adopt something that we can use that stays consistent. So we don't have to keep track of all the changing masses and things like that. So we're going to swap in all of our theory and stuff we understand about physics and kinematics and Newton's laws and all that stuff, energy, we are going to swap it for density, right? Sort of an analog. All right. The other thing that can be a little bit problematic is force. Okay. So instead of talking about forces, we are going to talk about pressure. Now, that symbol right there is a capital P. Sorry, I don't. I know you guys don't believe me, but I don't sit in my office and think of ways to make this harder or meaner. Yes. 3 lines? I don't know that notation. That's confusing because in physics, 3 lines means definition of. Yes. So the answer is no, I won't do that. Okay. So this is pressure. And this is density. Density. There we go. Okay. Now, interesting things about pressure. Obviously, pressure is related to force because it's a force divided by area. But the area is the area that the force is concentrated on. When you jump in a swimming pool and you dive to the bottom, what happens to your ears? Yeah, right? You start feeling that sort of pain in your ears, the pushing in of the pressure on your ears. Where's the pressure coming from? You're getting deeper and deeper into the water, so there's more water above you. The fluid has weight. So does fluid have mass? Yes. Keeping track of it's tough, so we don't want to do mass, we want to do density. And the more of it we get above us, the more we are forced upon by those fluids, right? And then now the area we're talking about, if you're down in the water and the pushing on it, it's just the area of your eardrum, right? So it's all that additional weight of the fluid above you pushing in on that little tiny area. No wonder you go, ow. And what do you do to fix it? Go back up. But if you're not going to go back up, you grab your nose and you right? You blow, and it kind of equalizes the pressure between the holes in your head and the outside world. Okay? And then the difference in pressure inside to out is 0, and it doesn't hurt anymore. Maybe you didn't think about this. I did this morning when I woke up. But you woke up immediately to a high pressure situation. You're in it right now. How much pressure are you under? Close. Atmospheric pressure. How much atmospheric pressure are you experiencing right now? 1. That doesn't sound bad. But now this is where things get bad. What are the units of pressure? Okay, look at the screen. I know I asked a loaded question. It's okay. It's going to be a Newton, because that's force, right? Divided by a meter squared. We're going to call this a Pascal for reasons you'll find out on Thursday. Okay? The symbol is PA, right? And that is the standard unit of pressure in physics, in the SI unit system. I know you don't believe me because you probably have never heard of a Pascal. What you have heard of are things like atmospheres, pounds per square inch, abbreviated to PSI. Now, a pound divided by a square inch. Is that a force divided by an area? Yes, it's just in stupid units, right? The atmosphere is one that chemists use a lot because they generally aren't really changing the pressure. If you're doing high pressure chemistry, that sounds fun, but I never got to do it. This is equal to 1.01 times 10 to the 5th pascals. So whenever you see 1 atmosphere, if you're sitting at the surface of the water, like at the surface of the ocean, you've got 1.01 times 10 to the 5th pascals of pressure being exerted on you. 14.7 pounds per square inch. So about 15 pounds for every square inch of surface area on your body. Little square inch on my body has almost 15 pounds of force being exerted on it. And so does this one. So does this one. How many square inches are there on the average human being? The answer is 2,000. Okay? 2,000 square inches of surface area. Each square inch feeling 50. How many pounds is that? What's 2,000 times 15? 30. 15 times 2 is 30, right? And there's a bunch of zeros, and if you add all the zeros up correctly, it's 30,000 pounds of force. No wonder you are cracking. No wonder you're feeling it. No wonder it's so hard to get. No, none of that's true. Some of it's true. You are cracking and you're feeling the pressure, but that's different. Why don't we feel that force, that 30,000 pounds? Yeah, you were born into it, right? And more importantly, the pressure inside you is the same as outside you. It's when those two things get out of sync that we start having problems, like when you jump into a pool. Because one of the things you did when you jumped into the water to dive down to the bottom is you closed all the holes in your face. Right? And you locked in a pressure at that point, and now you've gone down, and now it's more than 14.7, right? It's lower inside your body than it is outside in the water, and so which way will the net pressure be? In, and pushing in on your eardrums is no bueno. In physics, we think of, right, being, say at the bottom, I want to make something very clear from what I'm about to draw. You are not dead. I've been accused in my drawings of making people look like they are dead. You are not dead. Okay? You've gone down, okay? And you are at a depth inside of this pool, okay? Physicists are very weird. You know this already. And instead of calling this D, we're going to call it H. This is because in physics, we tend to think of the height of the fluid above you. Okay? So the depth of the water, we're going to call symbol H. The pressure at this point is a combination of the atmospheric pressure pushing down, P naught, okay, plus the pressure that is being caused by the water that you are in. That extra pressure is rho times G times H. Notice, pressure has units of what? Pascals. So your atmospheric pressure has units of pascals. So what are the units of rho GH? Pascals. But rho GH feels an awful lot like what? MGH, right? It's close. It's not MGH, but it's got a feeling. Stick that in your pocket for later. It's going to come up again. But this pressure, amazingly, only depends, well, okay, 3 things, but really only one thing. Does the pressure depend on what material you happen to be swimming in? Yes. So if you swap out your swimming pool water for, I don't know, honey, you have issues. Does it matter which planet we're on? Yes. Okay? But those two things more or less being the same on planet Earth, right? Little h is the only other thing this pressure depends on. So if you dive down, let's say 5 meters in the ocean, but you dive 10 meters into a swimming pool, where will you experience more pressure? Not the ocean. People tend to associate pressure with like the amount of water. Is there any volume or amount or any mass or anything in here? It is only the vertical amount of fluid that's above you, which is pretty darned amazing. I'll show you more about that on Thursday. Let's see, what's our schedule here? We have Thursday and Tuesday to finish up chapter 14, right? Because what's happening next Thursday? Your exam. So what's happening next Wednesday? The review for the exam, right? Tomorrow's lab, I have nothing planned. You're welcome to come and get help on your homework or not. I'm sure you have other projects that you're working on, other papers, other exams, and if you need to do that instead. When is your chapter 13 homework due? Saturday. When's chapter 14 homework due? Wednesday. So you want to get ahead. I'm giving you an option to get ahead. Have a good rest of the day.